I'm sitting here with this cool device called a Magic Eye vacuum tube. And it was used way back in the day with old radios in order to see how in tune they were, or if you needed to fiddle with the dial to get the station a little bit better. We're going to use it for something really different though. We're going to use it in order to see if we can put forces on some of the smallest pieces of the universe, namely electrons. In class, we have thrown stuffed animals around, we have pushed people, we have pulled carts, we have swung things on strings, and that's how we've put forces on stuff. But we've done it on big objects. It turns out you can actually put forces on really tiny things like electrons as well, and that's what we're going to do here right now. The tube is hooked up to something equally interesting looking, this rather scary setup of 24 9-volt batteries, which at the moment is giving about 235 volts. It's easier to see what's going on if you look at the tube from the side. This is what people on their old radio would have seen when they looked at it. But let's zoom in on the side of it. In addition to the glowing top, I hope you guys can see a glowing red piece of wire. And that's just red hot. That's not doing anything particularly interesting. It's actually acting like the filament in an old light bulb. In fact, it's not plugged into the 235 volt battery. It's plugged into the lab power supply. It's getting about 6.3 volts right now. Just like an old light bulb, that electricity makes a wire glow and give off light. And one of the other things it gives off is just electrons. They start flying off when things get that hot. In a light bulb, they don't really do anything. But in a vacuum tube, when you have that high voltage, you can actually set up an electric field which can make electrons fly from one place to another. They can get attracted from one place and repelled to another. So that's what's going on here. In the middle, the electrons are being created, and then they're being pulled to the outside. They're being pulled in every direction where you see the glowing. But it's always along the top of the tube, kind of outwards in that circle. And what they're hitting contains a special chemical, and that chemical, when it gets hit with electrons, it glows and it gives off light, which is called fluorescent. So everywhere there's electrons hitting that outside piece, that's where you're seeing. It's a bit hard to see with my camera. It's much easier to see on some of the pictures that go with this video. But the thing that's glowing is shaped like a cone. It's like an ice cream cone that comes down into a point. We're not going to be able to look at individual electrons, but there's beams coming out at every height in this cone as it goes to the outside. So what we're going to do is we're going to put a force using this coil of wire. And that's going to make the electrons, instead of going straight out, it's going to make them start to move in circles. Now we won't see an individual electron doing that. But because this is cone-shaped, the ones that are farther up, closer to the top of the tube, they are going to get to travel farther before they hit the side because it's wider up there. The ones that are down towards the bottom, they're going to go in similar paths, but because the cone is closer, they're not going to get to go as far. So it's going to give us all these beams of electron together. It's going to give us a circular pattern. And that circular pattern will have the same shape as what a single beam of electrons would. So in a moment, you're going to see me put the coil of wire over the tube. You're going to see how I'm going to control the magnetic field in that coil of wire. We're going to be able to make a magnetic field that goes straight down or up in this coil of wire, depending on how we set it up. And that's going to put that force on those electrons and make them start spinning. And we're going to be able to measure it. The electrons are actually very sensitive to magnetic fields. And I've got over here a coil of wire that if we pass electrical current through, we can have different magnetic fields. This thing here is called a potentiometer. It's going to allow me to have different amounts of current flowing through the coil, different magnetic fields. We can measure it with this thing here, which is an ammeter. So what I'm going to do is I'm now going to put my Magic Eye tube inside the coil, and we'll see what happens. So I've got the Magic Eye tube inside this coil of wire now. You can see it looks just the same with the straight sides of the two glowing regions. And that's because this coil of wire is not doing anything yet. It's not hooked up. Once I hook it up, I'm going to be able to control the amount of electricity going through with this thing, which adjusts the amount of electricity allowed through as I turn the knob. It's called a potentiometer. We'll be able to measure the amount of electricity, the amount of electrical current, using this meter, which is called an ammeter. And we're going to see electrons are affected by being in a magnetic field, which is going to exist in this coil of wire when electricity is flowing. So let's hook it up and see what happens. So just have to connect this wire. And watch the edges. As I increase the electricity, which I'm doing now, those edges start to get curvier and curvier. And that's because those electrons are having a magnetic force put on them. So I'm letting it off now. What I'm going to do is I'm going to stick this rubber rod, which is from the electrostatics experiment that we'll do later in the year. I'm going to stick it down in there, and we'll make the electrons curve to match its radius. And then we'll be able to get that radius outside of the tube. It's hard to get this lined up quite right, but I've got this rubber rod in here, and the curved edge of where the electron beam is hitting the screen has about the same radius as this rod. So we'll go measure that rod in a second, and we'll know the radius of the circle that that electron beam is being forced in. This is happening at 4.25 amperes of current, and the accelerating voltage that's sending those electrons out is 236 volts. And just to back the current off one last time so you can see how it goes back to the normal shape, letting the current down, and now removing it entirely. This device here is called a vernier caliper, and what it does is it helps us measure things that are hard to get a ruler around if we want to get diameters of things. The scales tell us the distance between those teeth. So we're going to go over to our rubber rod. We're going to stick the teeth in, and we're just going to read off that this is 1.3 centimeters. 1.25 actually. Okay, so since we know the voltage that we were accelerating those electrons at, we'll be able to calculate how fast they were going. In addition, because we now know the radius of the circle that they were starting to move in, we should be able to figure out the magnetic force that was applied to them. The way the lab was originally written, we would use the current to go and figure out then what the mass of the electron is. Since we don't know much about the magnetic force yet, I'm going to be happy just if we can figure out how big that force was. What force do you need to make an electron start moving in a circle?